My name is Joseph Onyango, lecturer from Railway Training Institute. Today we would like to have a topic on machines and utilization. Topic is DC machines. So we are starting from torque over DC motor. Torque over DC motor. This is where, for somebody who's doing diploma in electrical engineering, power option should start from in module 3. So, torque over DC motor is given by is given by T is equal to 60 PM all over 2 pi M, where PM is the mechanical power developed. Mechanical power developed. So today let's have something on machines and utilization. The topic is DC machines, and now we start from a subtopic of torque over DC motor. Torque over DC motor is given by T, which is equal to 60 PM all over 2 pi N, where PM is the mechanical power developed within the armature, and N is the speed in revolutions per minute. But PM can be evaluated by having back EMF multiplying armature current. The EB is just the back EMF, which is the same as the generated EMF by the armature. IA is the armature current. EB from dimensional constants will be equal to N phi PZ all over 60A. All over 60A, where P is the number of poles within the DC motor or within the magnetic circuit of the DC motor. Z is the number of armature conductors. And A is the number of parallel paths within the armature. Number of parallel paths within the armature. So this implies that our PM will be equal to N phi PZ all over 60A. Now we multiply with IA. Therefore, TB, therefore T, torque, therefore T, which is torque, is given by 60 all over 2 pi n. Now multiplying N phi PZ all over 60A. The whole of this multiplying IA. When this one is simplified further, this one is simplified further, we'll get this 60 will cancel that 60, n and n will also cancel. So we'll be remaining with 1 all over 2 pi A P Z P phi Z multiplying IA. But when a motor is already bought and it is within the premises or within where it is to be installed or already installed, you cannot be able to have P as a variable. P will be a constant because the motor is already with you. There is defined number of poles for that particular motor. And we have also, you cannot change the number of parallel paths within the armature. So P and Z, those ones will be constants. So this one will be equal to PZ all over 2 pi A. Now multiplying phi, multiplying IA. Phi is the flux per pole. Now this phi is from the field circuit of that particular motor. It is the field flux for that particular field circuit of that particular motor. And this one can be varied depending on what is done or depending on the magnetic circuit of that particular motor. So if phi can always be varied, and if you vary phi, the torque will also vary. You can also vary the armature current because when you have an armature circuit, you can include some resistances. When you include this, you can be able to vary armature current. And armature current also depends with the loading. So from this expression, we can say our T is directly proportional to phi, and directly proportional to phi IA. Therefore, T is equals to K phi IA, where K now here is equal to PZ all over 2 pi A. PZ all over 2 pi A. See from this expression, when you want to increase the torque on the motor, you can interfere or you can do something on the field flux per pole, or you can do something on the armature current. When those two are varied, then we can vary our torque. So T1 is proportional to phi 1 IA1. T2, that is torque 2, will be proportional to phi 2 IA2. So because we are working with the same motor, there is that constant of proportionality. So T2 divided by T1, the two constants will cancel. That is K. The two K's will cancel. We'll have T2 all over T1 will be equal to phi 2 IA2 all over phi 1 IA1. And this can be used for analyzing the working of a DC motor under two-torque analysis. Under two-torque analysis or under two-load torques. Under two-load torques. For a DC shunt motor, phi is normally practically constant. Practically constant. Normally practically constant. Therefore, T can be said to be proportional to IA. T can be said to be proportional to IA. For a DC series motor, phi is proportional. Phi is proportional to IA. That is before the magnetic circuit is saturated. That is before the magnetic circuit is saturated. That is, T will now be proportional to IA squared. That is, T will be proportional to IA squared. Speed of a DC motor. Speed of a DC motor. Speed of a DC motor. From AB equals to N phi PZ all over 60A. From this, we can make N the subject because N is the speed of the motor. So this implies N is equals to 60A multiplying EB all over P phi Z. 60A all over PZ. The whole of this is a constant. Now multiplying EB all over phi. Multiplying EB all over phi. Now 60A all over PZ is a constant, so we can replace it by, let's say, a constant K. Multiplying EB all over phi. From this expression, we can see, everyone, that speed N is proportional to EB. And N is inversely proportional to the field flux. So when you increase EB, N will be increased. When you increase field flux, N will be reduced. When you decrease field flux, N will increase. But the increase in N by the reduction of field flux cannot proceed until we check on the armature reaction. Because if you decrease the value of the field flux such that the effect of the armature reaction becomes critical, then the motor will not now operate. Therefore, reduction of field flux while trying to control the speed of a DC motor should also be done as we check on the armature reaction. This implies now N1 will be proportional to EB1 all over phi 1. And N2 will be proportional to EB2 all over phi 2. This implies what? N2, when it is divided by N1, will be equal to EB2 all over EB1 multiplying phi 2, phi 1 all over phi 2. Phi 1 all over phi 2. Phi 1 all over phi 2. So this is what will, the equation that we are going to use when analysis of the speed, when analyzing the speed of a DC motor. So there are instances you would like to increase the speed. So you must know what will happen to the field flux, what will happen on the back EMF. So from the equation, N is equals to, from the equation N is equals to KEB all over phi, which will be the same as K into EB can be found taking a case of, let's say, analysis of the most common DC motor, the shunt motor. So V minus IA RA will give us EB all over phi. So from this expression, we could deduce three methods of controlling the speed of a DC motor. Three methods of controlling the speed of a DC motor. So check on this. Now, if V is here, that is the voltage, input voltage to our motor. If you do something on the input voltage, if you try to vary that one, it will give you a change in speed. If you do something to the armature circuit, then there will also be a change in speed. If you do something on field flux, there will also be a change in speed of that DC motor. Therefore, this brings to us three methods of controlling the speed of a DC motor. Therefore, three methods of controlling speed of a DC motor are: one, control method. Amateur or rheostatic control method. 3. Voltage control method. So from these 3 methods, we would like to see how can we control the speed of various DC motors. We have DC motors, we have the series motor and the shunt motors. How can we control the speed of a shunt motor or a series motor with field control method? So we now move to in field control method for shunt motors, a rheostat is normally inserted in the field circuit of a DC shunt motor, as can be shown in the diagram below. As can be shown in the diagram below. So R that we have here is the rheostat that is inserted in this particular field circuit so as to control the current flowing through the field circuit, which we will call I shunt. Now, when we control I shunt, will be controlling the flux produced by the field coil. By the field coil. So from this it can be seen, this will now be called I shunt 2. This will be I2. And this will be IA2. Because originally there was no this rheostat in this particular circuit. By that time we had I shunt 1 flowing. We had I1 drawn from the supply. We had IA1 flowing through the armature. Now from this indication it can be seen now, for us to obtain I shunt 2, I shunt 2 will be equal to V divided by R shunt plus R. R shunt plus R. This I shunt 2 will be responsible for production of our phi 2. So I shunt 2 will be proportional to phi 2 before the circuit, before the magnetic circuit is saturated. For series motors, we have got some methods of controlling the flux in DC series circuit. So there are four methods of controlling the field flux. In a DC series motor. One, paralleling of field coils. So tapped field coils. There's a minute to get some